In this video we will discuss about motional EMF. So in last videos already you got the concept of EMF or induced EMF, that is when there is a change in magnetic field or change in magnetic flux linked with the coil, then in the coil there is a formation of some EMF that is called induced EMF. Now see, this motional EMF is also a kind of induced EMF which arises due to the motion of a conductor, or we can say due to the motion of some parts of a conductor. So here there is a rectangular coil PQRS. This one PQRS, that is a rectangular coil. Now in this rectangular coil, this one side is movable. This RS side is movable, it is moving. Suppose it is moving with a velocity v, okay, this side. So what happened is, as it is moving with velocity v in a uniform magnetic field B, this cross means this is a magnetic field, you know this one, that cross means it is into the plane of the paper. The direction of magnetic field is perpendicular to the plane of this paper, but it is inside, into. Now the length of this rectangular coil is L and this is X, the breadth. Now as the side RS is moving with velocity v, this X is a variable one, X is changing. So if X is changing, we can say that the area of the coil is changing. So if area of the coil is changing, before this was the area, so in this area the number of field lines, these cross lines are field lines, right? These field lines are passing through this area. So suppose initially, just an example, if 100 field lines are passing through the area, as this side is movable, the area is reducing, so the number of field lines linked with this area is reducing, okay, because the area itself is reducing. So we can say that there is a change in field lines, or we can say that there is a change in magnetic flux phi. So if there is a change in magnetic flux, what we know, that in this conductor there will be induced EMF, and as a result current will start flowing through this conductor. Okay, we will find out that induced EMF, and in this case this induced EMF is called motional EMF. So to find that induced EMF, we start with this phi is equal to BA. Okay, this formula you remember that flux equals to, you know already this one, no? Phi equals to what? It was B dot A. Now see here, this is the B means it is, as I told you, that it is a magnetic field perpendicularly inward to the plane of the paper. And area, if this is the area, then we know that if area is a vector, its direction is also perpendicular to this plane. Okay, so that means the angle between them is, you can take it as 0 degree, or you can take it as 180 degree, but in both the cases the magnitude of phi remains BA only. For 180 it will be minus BA, for 0 it will be plus BA, but we are dealing with this magnitude, it is BA only. Okay, so phi equals to BA. So BA means area means what? Length into breadth, so it is Lx. Then we have this formula from Lenz's law, E equals to minus d phi dt. So this E equals to minus d dt of phi. Phi means BLX. Now in this equation, which one is the variable? Only X is the variable, so rest term BL is coming out. This negative sign, okay, dx dt will remain there. Just a second, this one, minus minus d dt BLX, BL is coming out, so inside there will be minus dx dt. Okay, you put one negative sign here, minus dx dt. Okay, now the thing is that, see, in this minus dx dt, this one, we know dx dt is velocity, but here I have written minus dx dt as the velocity, because with respect to time x is changing, x is reducing, you can say. Changing means reducing, so to reduce that, this negative sign is indicating that reduction. Okay, so as a result, considering the whole negative sign with dx dt, I am writing velocity. Okay, so as I told you that here you you put one negative sign, this negative sign will come here. Okay, so minus dx dt as a whole will write velocity. So finally what we got, EMF E equals to BLV. This is the motional EMF. Okay, now we will find two more things from here. One is the power, very important one. In last time also in board exam this expression came to derivation of this power. Okay, so after induced EMF, what we know that there will be some induced current also. So current equals to EMF by R. The formula Ohm's law, V equals to IR. V means EMF or potential, right? So V by R it should be. So here in this case, in place of V, that will be EMF. So substitute the value of E, BLV. So BLV by R. Now again we have the expression for force, F equals to I into L cross B for a conductor. Now here L and B in every way that is perpendicular, because if you consider this length is like this, B is into the plane, so perpendicular. For this length, B is into the plane, perpendicular. For this length also perpendicular. So in every way the length and magnetic field are perpendicular. So if it is perpendicular, then cross B, cross means there should be LB sin theta. Theta is 90, so sin 90 is 1. So that is why what we are getting, F equals to only ILB. Okay. Now in place of I we will substitute this value, LB will remain as it is. So from this F comes like this, B square L square V by R. Then power dissipated. The power, we have the formula F into V, force into velocity. So force, you substitute this, velocity is V, so V into V will become V square. So finally the expression for power is this one. Okay. So that is related to motional EMF. Another kind of motional EMF we will get here, that is when a rod, conducting rod, moving in a magnetic field, moving in a perpendicular magnetic field, then also some induced EMF is generated in the rod. Suppose here this is the rod, okay, PQ, conducting rod, and this cross field is the magnetic field, means it is into the plane of the paper. Now as this rod is rotating, keeping this point fixed, P fixed, it is rotating like this, this rod is rotating like this. So if it is rotating, it is actually cutting the magnetic fields, because magnetic fields are perpendicular. Can you follow? Magnetic fields are perpendicular to the plane of the paper. Just imagine that magnetic fields are perpendicular to the plane of the paper. Okay, and this rod, it is rotating on which plane? On this plane. So if it is rotating and if magnetic fields are perpendicular, this rod, it is actually cutting this magnetic field. And in this case, whenever a conductor cuts through a magnetic field, then it produces induced EMF. And this thing is practically, we use this thing in many cases. Suppose, just an example, when a train moves, the body of train is made of conductors, right? So when a train moves with heavy speed, with high speed, we know that magnetic field of earth, BE, in last videos you got this one, it has two components, right? One is horizontal component, BH, one is vertical component, BV. So when in a train, suppose this train is moving like this, it is cutting the vertical component, this is BV, vertical component of magnetic field, right? So this train, in this train or in the track of the train, you can say there is a formation of some induced EMF or induced current. That current is finally used by signal department to you can say detect whether in the track train is running or not. If the train is running, it is forming some current, some EMF, and that EMF is detected by the control department. Okay, so the thing is like this only here also, that this is the rod is moving in a magnetic field which is perpendicular, so it is also cutting the magnetic field, and as a result there will be formation of induced EMF. We are going to find out that induced EMF. That is also a kind of motional EMF, okay, because the conductor is in motion, no? So that is why the induced EMF is produced. Anyways, some approximations are also there. Okay, let's see. Okay. So here you can see the length of the rod is L. Okay, then it is moving from PQ position to PQ dash, suppose, with how much angular speed? Omega. In this PQ to PQ dash, it has subtended an angle alpha at the center, and this is the length of the rod, means like it is the radius of the circular path, isn't it? So now we know that this arc QQ dash, that is equal to radius into angle subtended, means L into alpha, this arc QQ dash. Okay, now considering this arc almost as a straight line, we can take it as a triangle. That is the approximation. And if we take it as a triangle, it will have an area half into height into base. So the base is L, height is this arc, which is L alpha, and into half. So that will give us the area. And why we need the area? To find out the induced EMF. Okay, then let us see the derivation part. So just like the previous derivation, E equals to what? D phi dt, we know this one. Then d dt of phi means BA, just like the previous one, B into A. Okay, alright, because here you see the area and magnetic field are perpendicular, no? Perpendicular in the sense, this much is the area, the direction of area is perpendicular to the plane, and magnetic field is also perpendicular, so angle will be either 0 or 180. So in both the cases, the magnitude in any way is coming as BA. So d dt of BA. Now this B is coming out, inside integration we have dA dt. Now the part of this area, dA dt. So area, just now I told, it is half into base into height. Base is L, height is LA. Okay, so this is coming like this. This value of area will be substituted here. So it will be, B will remain outside, d dt of A, okay, which gives us half B L square dA dt. A, what was that? It was the angular displacement. So if A is, you know this one, if A is the angular displacement, then dA dt is equal to angular velocity, means omega, or angular speed. In class 11 you got this one. Okay, so if here we substitute omega, the formula becomes BL square omega. That is the formula for induced EMF. Okay, then the next topic, eddy current. Okay, so eddy current means there is a, if a metal block, okay, suppose in previous discussions you already got, suppose if this kind of coil we have, if it is connected with a galvanometer, if there is a magnet, this is Faraday's law, no? And if the magnet is in motion, either moving this side or moving that side, we get that the flux linked with this coil is changing, right? And as a result we get some induced EMF here. Now in eddy current also it is a kind of induced current, but there we don't take this kind of coil. Instead what we take some metal block. Suppose this is a metal block of metal, okay, and this block of metal, it is kept in a varying magnetic field. Varying means the magnetic field intensity is changing, or this block is kept in a magnetic field where this block itself is, suppose, moving, or the magnetic field is, you can say it is a changing magnetic field. So in both the cases, whether this thing is moving or the magnetic field is a changing one, varying magnetic field, in both the cases, in this block of metal there will be formation of some current loops, some loops of current, induced current. In the previous case there was a conductor and current was formed in the conductor itself, but here the current is formed in the block, this metal block. Okay, and how these currents are formed? They are forming some in the form of some circular loop, means like this, then like this, then like this. So this is like eddy we know, right? Like whirlpool which is created in water when we throw some stone or something. In that case, that is called eddy also, no? So this current is called eddy. The reason is this one, because in conductor is a bulk thing, right? Means it has a particular volume, it has a area. So for this bulk thing, this is one current loop, another loop, another loop, it goes on like this. This is called eddy current. So eddy current, here it is written that it is nothing but it is the induced current or induced circulating current produced in a metallic block itself due to the change in magnetic field. Okay, changing magnetic field or magnetic flux linked with the metallic block are called eddy current. So whenever there is a varying magnetic field, because we know that induced current is produced only when there is a change in magnetic field or change in magnetic flux. So that is why this block, whatever we consider, either it should move or the magnetic field, means suppose this is north pole and this side there is a south pole. Okay, so from this north pole to south pole field lines are coming like this. Okay, and this, if this is a varying magnetic field or if the block is moving, suppose here, then what will happen? The field lines linked with the block, it is changing, so there will be induced current. Alright, now this eddy current is of different use. In some cases eddy current is not desired, like in case of transformer and all, this eddy current is not desired. Because sometimes we know that current is produced means it is some form of energy is lost. So in some cases where we don't need eddy current, there if it forms, then it is not desirable. Okay, and in some cases eddy currents are in fact used for some constructive purposes also. Suppose for example, just a second, suppose so in some cases where eddy current is required, suppose you go through this one. Okay, uses of eddy current. One use is induction furnace. Now what is this induction furnace? It's a kind of furnace where alloys are formed, and how eddy current is used there, just an example I am giving. Suppose alloys means there should be some metals in molten state, because alloy means combination of metals, no? So to melt those metals, eddy current is used. Suppose a block of metal, it is kept in a varying magnetic field, then there will be formation of circulating current loops, and this current will further produce what? Heat. We know heat equals to I square RT, right? So this heat, this heat due to this eddy current will melt this metal, and as a result, in this way we can take few metal blocks which will be melted using eddy current when they are kept in a magnetic field, varying magnetic field, and in that way those molten metals can be mixed to form the alloys. So in induction furnace, then in brakes of train, this this induced current phenomenon is used, or induced current technique is used. That one, just the theoretical part I am telling you. Suppose when the wheels of the train that is moving. Okay, another very important thing, eddy current, since it is induced current, the direction of eddy current is such that it opposes the cause of induction, just like Lenz's law. In Lenz's law we know this one. So suppose this is the wheel of a train, it is moving or the train is moving. Okay, now suppose when brakes has to be applied, right, there should be some this is moving, right? So suppose what happened is, a magnet, when brake is applied, a magnet comes in the comes near this wheel. It may be a permanent magnet, it may be an electromagnet also. Electromagnet means a solenoid. When current flows through this solenoid, it behaves like a magnet, no? So these are electromagnet, means with the help of current only they are getting the magnetizing property, but these are permanent magnet. So any one of this, suppose it is brought when the brake is applied near the wheel. So as a result, what will happen? There is the wheel is in motion, the magnetic field suddenly appears, then the flux linked with the wheel will change because the wheel is rotating, no? So with the rotation, the number of field lines linked with this field lines will pass through this. So the since it is rotating, with the rotation of it, number of field lines linked with the wheel is changing, and the wheel is completely a metal, completely made of metal. So in this wheel there will be formation of eddy current. And we know that eddy current, just now I told you that eddy current means it is opposing the cause of motion or cause of induction. So in this case, what is the cause of induction? The motion of the wheel. If the wheel is not in motion, there will be no induced current. So the eddy current produced will oppose the cause of induction, means it will be formed in such a way that it opposes the cause of induction, means it opposes the motion of the wheel, and as a result brakes will be applied. Because brake means the main purpose is to stop the train, so the main cause of induction is the motion of the train or motion of the wheels. So the eddy current which is produced in the wheel, it will try to oppose the motion of the train, and as a result brakes will be applied or the train will stop. Okay, so this is one of the use of eddy current. So this kind of one or two uses you can see. Two uses already I told you. You can see few more from any book. Okay, thank you.